Mercury stands as our solar system's most difficult planet to reach, despite being Earth's second closest neighbour. This might seem puzzling at first. Shouldn't the nearest planets be the easiest to visit? The answer reveals fascinating truths about the extreme challenges facing space exploration. What makes this small world so incredibly hard to visit? Is it because Mercury sits too close to the Sun? Could it be the planet's extreme temperatures? Or does the composition of the planet itself create the problem? If you like the content, consider liking and subscribing to the channel, because today we venture into the hidden mysteries of space travel, and what we uncover will change everything we thought we knew about reaching other worlds. The truth behind this journey will surprise you and reveal secrets that reshape how we explore every planet in our solar system. Most people believe Mars is our nearest planetary neighbour after the Moon, but this popular belief is actually incorrect. Venus holds that title. At its closest approach to Earth, Venus sits just 25 million miles away, making it our nearest planetary companion. Mercury comes in second place at 48 million miles away from Earth at its closest point. Meanwhile, Mars typically maintains an average distance of about 55 million miles from our planet. Mars only gets closer than Mercury during a special event called perihelion, which happens once every 26 months. During these rare alignments, Mars closes to just 36 million miles away from Earth. However, for the vast majority of the time, Mercury is actually nearer to us than the famous red planet. This surprising fact challenges many common assumptions about our solar system. When humanity began exploring the solar system's planets with robotic spacecraft, Venus received the first visit in 1962. Mars followed soon after in 1965, and the giant planet Jupiter was reached in 1973. However, Mercury didn't receive its first visitor until 1974, when the Mariner 10 space probe finally arrived at this challenging destination. What's even more surprising is what happened next. After that single mission, Mercury was essentially ignored for 3 full decades. During those 30 years of neglect, numerous missions were launched to explore Mars and the outer planets. Space agencies even sent probes to study asteroids and faraway comets, but Mercury received no visitors at all. Why did this happen? Was it because the Mariner 10 exploration probe had given us all the information we needed from Mercury? Absolutely not. The Mariner probe only managed to fly past Mercury 3 times during its mission. During those 3 brief flybys, it only succeeded in mapping about 40 of the planet's surface. Scientists remained very interested in continuing to study this mysterious planet. The real reason for the 3-decade gap was simple but profound. Mercury presented unique challenges that made it the hardest planet of all to visit. Chapter 1: Mercury's Twin. Challenges: Heat and Speed. The reasons why reaching Mercury is so difficult can be divided into 2 main problems: extreme temperature and incredible speed. Let's explore each of these challenges. Mercury holds the distinction of being the closest planet to the Sun in our solar system. Because of this proximity, the temperature on Mercury's surface regularly reaches a scorching 806 degrees Fahrenheit, 430 degrees Celsius. These temperatures are extraordinarily high and can easily destroy the delicate circuits and electronic components inside any space exploration probe. To survive these conditions, ships sent to planets closest to the Sun must be equipped with special protective panels. These panels shield the spacecraft's sensitive equipment from the Sun's scorching temperatures. Engineers typically place these protective panels on only one side of the ship. Using the communication antennas as a pivot point, mission controllers keep these panels constantly pointing at the Sun, creating a heat shield that protects the ship's vital instruments from damage. The second challenge is actually the most crucial reason why sending ships to Mercury is so incredibly difficult. The proximity to the Sun creates a speed problem. As you know, all objects with mass create a force of gravitational attraction that pulls other smaller objects toward them. The Sun is by far the most massive object in the entire solar system, containing 99.8% of all the mass in our cosmic neighborhood. This enormous mass means that as spacecraft approach the Sun, they accelerate more and more until they reach speeds where controlling them becomes extremely difficult. This acceleration problem has caused the loss of numerous space probes in the vicinity of the Sun over the decades. Maneuvering such a rapidly accelerated ship using only rockets is an incredibly challenging task to accomplish. The problem is made worse because space exploration probes typically don't carry very much fuel. They carry limited fuel because they're much smaller than human-crewed spacecraft, and every kilogram of mass matters tremendously in space missions. When engineers design spacecraft, they always try to keep everything as light as possible. This isn't just about good engineering practice, it's an absolute necessity. The heavier a ship weighs, the more fuel it takes to get it off the ground. And the more fuel you need, the more expensive the mission becomes, which is definitely not attractive if you're working with a tight budget. There's another important consideration. The more fuel placed in a space exploration probe, the less space remains available to place scientific instruments. Those instruments are, in the end, the most important part of the mission. They're the reason we're going to space in the first place. For 30 long years, scientists and engineers struggled to find any practical way for a probe with limited fuel to handle the extreme speeds required to reach Mercury safely. But that all changed in 1985 when a brilliant solution emerged. In 1985, scientist Chen-Wan Yen, a graduate of MIT with a degree in nuclear physics, proposed an innovative way to reach planet Mercury using the technology available at the time. Chen-Wan Yen used his extensive knowledge in orbital mechanics and developed a very particular route. In this route, a spacecraft could travel an enormous distance passing through several planets. These planetary encounters would slow the spacecraft down enough to be captured by Mercury's gravity, and the probe would accomplish all this using very little fuel. Instead of sending a spacecraft directly to Mercury, which would require massive amounts of fuel, Chen-Wan Yen's new route charted a much longer path. In this plan, the spacecraft would have to circle the Sun approximately 15 times before finally reaching Mercury's orbit. The probe in charge of carrying out this complicated and lengthy mission would be called the Messenger Space Probe. To achieve this remarkable feat, the spacecraft would use what's called gravitational assistance from Earth, Venus, and Mercury itself. The flight plan called for passing through Earth's vicinity once, Venus twice, and Mercury 3 times. With each carefully planned flyby, the average speed of Messenger relative to the Sun would gradually increase. However, and this is the clever part, the speed of the spacecraft relative to Mercury itself would decrease. How does this seemingly contradictory situation work? Imagine you want to jump onto a moving train from a moving car. The train travels at 60 miles per hour along tracks parallel to Main Street. It will pass through the general store precisely at 1 p.m. You're prepared for action, parked along Main Street in your car. At 12:59:30, you start accelerating down the street to intercept the train. Your car's starting point is closer to the general store than where the train currently is. However, the train is going faster at 60 km/h, and both vehicles are moving in the same direction. As you accelerate up to 10 mph relative to your starting point on the street, you're actually going only 50 mph relative to the train itself. When you increase your speed relative to your starting point, the store, your speed relative to the train decreases. You're getting closer to matching speeds. You carefully calculate your acceleration to pass the store at precisely 60 mph at the exact moment the train passes. At that moment, you'll be traveling at 0 mph relative to the train and 60 mph relative to the store. You've matched the train speed perfectly. Similarly, the Messenger exploration probe used the gravitational assistance of planets to accelerate relative to the Sun, while simultaneously getting closer and closer to matching the orbital speed of Mercury. Once Messenger approached Mercury at the right speed, it could fire its main engine just enough to be captured by the planet's gravity and begin orbiting it successfully. Messenger was a relatively small exploration probe that launched on August 3, 2004. The spacecraft measured just 1.3 meters wide and weighed just over 1 ton. Despite its compact size, the probe carried sophisticated instruments for studying Mercury. The probe had a propellant thruster system to help it maneuver and control its direction during the long journey. The spacecraft also featured a specialized heat shield that protected its sensitive equipment from the high temperatures near the Sun. Additionally, it had 2 solar panels that, unexpectedly, scientists cleverly used as solar sails. These panels helped slow down the spacecraft's speed a little bit due to the solar wind. The Sun continuously emits solar radiation that spreads throughout the entire solar system. This radiation falls on spacecraft and pushes them very slightly. Though the thrust from the solar wind is tiny and typically doesn't significantly influence spacecraft trajectories, it made a difference for Messenger. Because the journey was going to be so long and last so many years, even this small assistance helped slow down the probe. Scientists tried to keep the solar panels pointing at the Sun at all times, which helped the probe save a lot of fuel and extend its useful operational life. Messenger made all its planned orbits correctly and without major complications. It passed through Earth's vicinity, then Venus twice, and finally approached Mercury 3 times. On March 11, 2011, it was successfully captured by Mercury's gravity. Messenger's entire route covered approximately 4.9 billion miles, 7.185 million kilometers. The journey took approximately 7 years to complete from launch to Mercury orbit insertion. Once Messenger reached Mercury's orbit, it began to perform eccentric orbits. These orbits alternated the spacecraft's distance between 125 miles, 200 kilometers, and 9,320 miles, 15,000 kilometers from Mercury's surface. This unusual orbit pattern was necessary because Mercury's surface acts as a giant solar mirror that radiates tremendous amounts of heat into space. If a spacecraft stays too long too close to Mercury, even with a heat shield, it could suffer damage to equipment or, in the worst case, cause complete spacecraft failures. The Sun has a brightness 7 times more intense at Mercury than at Earth. Because of this extreme radiation, mission planners decided that the probe would perform eccentric orbits. These orbits would allow it to approach and move away from Mercury periodically, giving it time to cool off from the high temperatures reflected by the planet's surface. During the next 4 years, the Messenger probe sent back thousands of photographs of Mercury's surface. These images provided essential information that helped scientists understand the planet's chemical composition, the geography of its surface features, and its internal structure. Finally, on April 30th, 2015, the fuel of the Messenger probe ran out completely. The scientists in charge of the mission decided to crash the ship into Mercury's surface, thus ending one of the most important planetary missions in space exploration history. Thanks to the Messenger mission, scientists achieved a significant discovery. In the images sent by the probe, researchers observed indications that could demonstrate the existence of frozen water at the poles of Mercury. This was an astonishing discovery because Mercury is so close to the Sun. Currently, the European Space Agency, ESA, and the Japanese space agency, JAXA, have launched a new mission called Bepi-Colombo. This mission will be responsible for revealing once and for all whether Mercury can have water or not. It is estimated that Bepi-Colombo will reach the orbit of Mercury in 2025. Chapter 2. Why Mars remains so difficult to reach. In addition to Earth, Mars is the planet with the best conditions to potentially host humans. Space agencies such as SpaceX and NASA are actively planning to take the next generation of astronauts to the Red Planet. However, it has not yet been achieved. Why is it so difficult to get to Mars despite our advanced technology? During the space race in the 1960s, NASA successfully completed 6 missions to the Moon that placed a total of 12 astronauts on the surface of our natural satellite. Having gone to the Moon several times nearly 5 decades ago, and being used to seeing astronauts travel to space almost routinely for extended stays on the International Space Station, it's tempting to think that sending humans to Mars should be perfectly achievable today. However, as of 2022, seeing the first humans walking on the Red Planet still seems to be distant. Science and technology tell us that sending human beings to Mars constitutes a challenge of enormous difficulty and complexity. This challenge is far beyond everything that has been done so far in the entire history of human space exploration. But there's one reason from which almost all other difficulties are derived: distance. We see astronauts frequently travel to space, particularly to the International Space Station, ISS. Before the ISS, for many years, cosmonauts traveled to the Mir station aboard Soyuz ships. Currently, Chinese taikonauts travel frequently to the Tiangong space station. Popularly, people have the impression that the destinations of these missions are very distant. However, the typical altitudes at which these stations and spacecraft orbit Earth are just a few hundred kilometers. The ISS, for example, orbits the Earth at an altitude that is equivalent to the distance in a straight line between Madrid and Almeria in Spain, about 400 kilometers. This space region to which humans routinely travel is within the so-called region of low Earth orbits. Technically, we call this region LEO, low Earth orbit. Lunar man travel involves traveling far beyond LEO orbits. The Moon orbits our planet at an average distance of about 380,000 kilometers, which is roughly 1,000 times farther than the altitudes of these low Earth orbits. A crew and their spacecraft are put into orbit around Earth shortly after launch. On the Apollo missions, the distance to the Moon was covered in about 3 days of travel. In the case of Mars, the situation becomes dramatically different. Going to Mars involves moving from a geocentric mission centered on Earth to a heliocentric orbit centered on the Sun. This represents a massive leap in the distances involved. Although the maximum and minimum distances between Earth and Mars vary within a specific range, the minimum possible distance is about 55 million kilometers. This closest approach distance is achieved every 26 months when Mars and Earth have an approach window that lasts just a few weeks. These are absolutely huge distances compared to all human-crewed missions to space so far. The maximum distance to Mars is approximately 1,000 times greater than the distance between Earth and the Moon. It's also approximately 1,000 times greater than the distance separating Earth's surface from the LEO orbits to which astronauts typically travel. In other words, a single trip to Mars is equivalent in distance to making 1 million trips to the ISS space station. To truly appreciate the scale of the problem, let's compare 2 human-crewed missions using round numbers: an orbital mission around Earth for a single crew member, and a lunar mission for 3 crew members. We'll start with the first orbital mission of the Mercury program of the early 1960s, John Glenn's historic Mercury 6 flight. In this mission, a 120-ton Atlas rocket with a height of 29 meters was used. it managed to put a useful mass of just 1.2 tons into orbit at an average altitude of 200 kilometers around Earth. The cargo was a Mercury capsule with its single crew member, who remained in space for only 5 hours. Now let's see what changes when we have the Moon as a destination about 1,000 times farther away. In the case of Apollo 17, the last lunar exploration mission, its command and service module plus its lunar module added up to about 50 tons total mass. These were launched to the Moon by the mighty Saturn V rocket, which weighed about 3,000 tons and stood 110 meters tall. The mission had a total duration of about 12.5 days. During this time, 2 of its 3 crew members remained on the lunar surface for just over 3 days, while the 3rd astronaut remained inside the command module, orbiting the Moon throughout the surface activities. We can see that the quantitative leap needed when we want to go to another world that is 1,000 times beyond the low orbits of Earth is enormous. The useful payload to be launched increased from 1.2 tons to 50 tons, more than 40 times larger. Meanwhile, the size of the launch rocket grew from 120 tons to 3,000 tons, 25 times heavier. Now compare all this to what a mission to Mars would require. For a realistic Mars mission, the crew would consist of at least 6 astronauts. The mission duration, taking as an example the approaching window in 2037, would be 174 days for the outbound journey, 201 days for the return journey, and a stay of 539 days on Mars itself. Such an extended stay on Mars would be necessary to wait for the relative positions between Mars and Earth to be optimal for the return journey with minimal fuel expenditure. This positioning saves the mission from needing to transport hundreds of additional tons of fuel. The total mission represents 914 days of being away from Earth, or approximately 2.5 years. This is an incredibly long time for humans to be isolated from their home planet. As we can see, the jump between the Moon and Mars is absolutely enormous, doubling the crew size and extending the mission duration to about 73 times. That of the longest lunar mission means the need to provide and transport about 150 times more supplies than a Moon mission required. A longer duration of interplanetary travel means the need to provide the crew with much better protection against cosmic radiation. This is achieved in part by adding even more mass to the ships through specialized shielding. Currently, this radiation protection problem is not entirely solved, and scientists continue to work on better solutions. Another serious problem with long-duration missions is that equipment breaks down over time. Either the durability of the equipment will have to be substantially improved, or crews will need the ability to replace broken items with spare parts. These spare parts will also have to be transported to Mars, which implies carrying even greater mass. Cargo spacecraft visiting the ISS can be restocked with spare parts when something goes wrong on board, but this option will not be possible on a mission to Mars. Anything that can possibly break will have to be repaired using tools and spare parts already on board the spacecraft. Experience tells us that braking a heavy train is much more difficult than braking a light truck. The train has more mass and therefore needs more time and distance to stop. Similarly, sending more mass to Mars also means transporting more fuel to accelerate all that cargo toward Mars. But it also means carrying more fuel to slow down when the ship reaches the planet, and you need additional fuel for the return journey to Earth. We're talking about hundreds of tons of fuel that will have to be carried to Mars in some form. One option that some scientists have proposed is to use the minerals and gases trapped in the Martian soil to produce fuel on site. However, so far, no system has been successfully tested that can reliably do this. Until we can prove that something like this is actually possible, the only option remains to carry all our own fuel from Earth. For the distances we've discussed, as well as for the complete round trip, a Mars mission will require carrying between 850 and 1,250 tons of fuel in total. This is an absolutely massive amount when you consider that the entire International Space Station has a mass of only about 420 tons. A ship with which we are very familiar, the Space Shuttle, could only send into space between 15 and 25 tons approximately, depending on the altitude of the final orbit. With the most powerful ships available today, taking all that required fuel into space would require us to make about 10 separate trips at minimum. Thus, we can already understand intuitively that a single rocket will not be sufficient to send a mission to Mars. Instead, several rocket launches will be required as powerful or more powerful than the Saturn V rockets of the 1960s. These launches will be needed to assemble in space different propulsion elements, fuel modules, habitats, and ships. These components will have to be sent to Mars separately and in advance of the main crew spacecraft, which would be sent last. The Saturn V was retired from service after the Apollo program ended, but it still holds the record today as the most powerful operational rocket ever built. It was capable of putting just over 120 tons into low orbit around the Earth and could send 50 tons to the Moon. It had to be specifically designed and built to accomplish the goal of reaching the Moon. The only rocket capable of potentially dethroning the Saturn V could be NASA's SLS rocket, Space Launch System, which may have similar or perhaps somewhat superior performance. A time of 539 days in weightlessness profoundly affects human physiology. This is especially worrying when you're arriving on a planet where no one can provide you with medical assistance if something goes wrong. The rotating cylinder-shaped cabins with artificial gravity that you see in science fiction movies don't exist today. Therefore, astronauts who go to Mars will suffer from weightlessness throughout the entire mission. Scientists don't yet know precisely how astronauts will recover their physical capabilities when they finally reach Mars. For psychological reasons, 2.5 years is an extremely long time to be away from home. Earth will appear to the crew as nothing more than a star-like point of light for most of the voyage. It will be barely noticeable in the Martian night sky. The crew will have to live in a condition of permanent confinement in a small space. They'll experience constant stress and face the impossibility of maintaining fluid, real-time conversations with their loved ones on Earth due to the signal's travel time. Remember that radio signals travel at the speed of light, which is the absolute speed limit in the universe. But even at that incredible speed, communications have a delay of about 8 minutes between message and response due to the enormous distances the signals must travel. Having a natural, real-time conversation with a loved one from Mars will be practically impossible. Although some enthusiastic and optimistic people claim that humanity already has all the technology and everything needed to go to Mars right now, science tells us that we are not completely ready yet. The difficulties and challenges that arise from interplanetary travel are still considerable and difficult to overcome. However, we may indeed have the basic technology to eventually achieve it. We primarily need the budget and sufficient time to plan everything properly. NASA has estimated that with modern science and technologies, it will be possible to take the first humans to Mars before the end of this century. Chapter 3: Jupiter. The challenge of speed and radiation. Jupiter is the most visited gas giant in space exploration. 9 spacecraft have reached it, yet only one has ventured into its dense atmosphere to study its interior. The planet Earth's immense gravity both aids and complicates missions. While it helps spacecraft enter its influence easily, slowing down enough to remain in orbit is difficult. Voyager 1 and 2, for instance, travelled too fast to be captured without powerful rockets, which early probes lacked. Later missions like Galileo and Juno carried engines to break into orbit successfully. Landing on Jupiter is impossible, It lacks a solid surface. Its gaseous layers grow denser with depth until crushing pressures destroy any probe. The radiation belts surrounding Jupiter are equally lethal, causing severe damage even to hardened spacecraft. Galileo, for example, suffered radiation failures during its long mission. Pioneer 10 reached Jupiter in 1973 and 11 followed in 1974. They captured the first close-up images of Jupiter and its four largest moons, Europa, Io, Callisto, and Ganymede, revealing stormy clouds and a massive magnetic field so vast that all other planets could fit within it. The probes discovered Jupiter-S radiation belts and confirmed that beneath its upper gases, the planet is mostly liquid metallic hydrogen under extreme pressure. Pioneer 11 also provided the first detailed images of the Great Red Spot and Jupiter-S poles. Voyager 1 photographed Jupiter in 1979, passing only 349,000 kilometers from its center. Its close approach revealed new moons Adrastea, Metis, and Thebe, and discovered the planet's thin ring system, previously unseen from Earth. The probes captured the first clear views of the Great Red Spot as an enormous anticyclone and observed intense volcanic activity on Io Earth, as first known extraterrestrial volcanoes. On Europa, they identified vast ice plains with cracks hinting at a subsurface ocean, making it one of the top candidates for extraterrestrial life. Launched in 1989, Galileo became the first probe to orbit Jupiter and send a descent module into its atmosphere in 1995. The entry probe transmitted data for nearly an hour before being destroyed by heat and pressure exceeding 22 Gray and 153 C. Galileo-S orbital mission revealed ammonia clouds, confirmed extreme volcanic activity on Io, and detected strong magnetic fields around Ganymede and possibly salty oceans beneath Europa, Ganymede, and Callisto. When its mission ended in 2003, Galileo was deliberately plunged into Jupiter to prevent contaminating Europa. Arriving in 2016, Juno studies Jupiter-S gravity, magnetism, auroras, and atmospheric composition to understand its formation. It orbits on a radiation-avoiding path, mapping the planet's deep structure and searching for evidence of a solid core. When its mission ends, it too will dive into Jupiter's atmosphere to avoid contaminating its moons. Chapter 4: Saturn. The distant giant Saturn lies 1.3 billion kilometers away so far that spacecraft must rely on nuclear batteries rather than solar panels. Only 4 probes have reached it, and just 1 entered its atmosphere. Pioneer 11 in 1979 gave the first close-up photos, discovering new moons and additional rings. Voyager 1 and 2 later revealed Saturn's yellow clouds, methane-rich moon Titan, and icy geysers on Enceladus. This mission revolutionized Saturn science. Cassini discovered new moons, observed massive storms, and revealed that Titan has rivers, lakes, and seas of liquid methane. The Huygens lander touched Titan's surface in 2005, showing hills, drainage channels, and rounded ice pebbles under 179 C temperatures. Cassini also detected powerful geysers on Enceladus, erupting water vapor and organic material from a subsurface ocean, 30–40 kilometers below its icy crust, making Enceladus one of the most promising places for life. To prevent contamination, Cassini was deliberately crashed into Saturn in 2017. NASA's Dragonfly mission, set for launch in 2027, will send a drone to explore Titan's surface directly. Chapter 5: Uranus. The tilted world. Uranus is the only planet that spins on its side tilted 97.7, giving it 42 years of daylight followed by 42 years of darkness. It's the third largest planet, with an atmosphere rich in hydrogen, helium, methane, and ammonia. Despite its strange properties, only Voyager 2 visited Uranus in 1986, performing a quick flyby. It found a frigid atmosphere of 224 C, complex cloud layers, and a magnetosphere oddly tilted like the planet itself. Uranus' sideways rotation likely resulted from a colossal collision early in its history. Reaching Uranus is difficult. It lies 3 billion kilometers from the Sun, requiring nuclear-powered spacecraft and journeys lasting up to 15 years. Communication delays exceed 20 minutes each way. Long mission durations make maintaining scientific teams and technology continuity a challenge, as seen with the now obsolete Voyager data systems. Although Uranus resembles many exoplanets discovered in our galaxy, NASA currently prioritizes Neptune for future missions. Chapter 6. Neptune. The farthest giant, Neptune, 4 billion kilometers away, remains the least explored planet visited only once by Voyager 2 in 1989. Voyager 2 revealed Neptune's Great Dark Spot, a hurricane with winds surpassing 1,000 km/h, the fastest in the solar system. It discovered 4 rings and 6 new moons. Neptune's rings are dense with dust, hinting at high meteorite activity. Triton, Neptune's largest moon, orbits in reverse and likely originated in the Kuiper Belt. Voyager 2 found geysers of liquid nitrogen erupting from its surface, showing that volcanism doesn't require molten rock. Triton's young, uncratered terrain suggests ongoing geological activity. It's one of the few bodies in the solar system alongside Earth, Io, Europa, Enceladus, Titan, and Venus known to be volcanically active. Because of Triton's potential subsurface ocean, NASA's Outer Planets Assessment Group prioritizes a Neptune mission over Uranus. A possible launch between 2028-2030 using Jupiter's gravity could reach Neptune around 2043. Chapter 7. Pluto, the distant dwarf. Once the 9th planet, Pluto orbits more than 6 billion kilometers from Earth. Only the New Horizons mission has explored it. In the 1970s, NASA planned the Grand Tour missions to visit all outer planets, but cost concerns cancelled the Pluto leg. The Voyager probes could have continued to Pluto after Saturn, but scientists chose instead to fly by Titan. For decades, Pluto remained untouched. Triton's discovery of active geysers revived enthusiasm for Pluto, believed to be its twin in the Kuiper Belt. With Charon's discovery in 1978, a mission could explore 2 worlds at once. After several cancelled proposals, NASA approved New Horizons, launched in 2006. Using Jupiter's gravity assist in 2007, New Horizons sped toward Pluto, arriving on July 14, 2015. It passed within 12,500 km of the surface, revealing a surprisingly active, ice-covered world with possible underground oceans and nitrogen glaciers. Pluto's mountains, plains, and recent geological features suggested internal heat and complex chemistry. After completing its flyby, New Horizons continued into the Kuiper Belt, becoming the only spacecraft to explore such distant regions. From Jupiter's crushing gravity and radiation to Saturn's icy moons, Uranus' sideways spin, Neptune's supersonic winds, and Pluto's frozen isolation, every world presents unique challenges. Exploring them demands precision, endurance, and innovation missions lasting decades, surviving extreme cold, radiation, and vast distances. Yet each mission Pioneer, Voyager, Galileo, Cassini, Juno, and New Horizons has proven that human curiosity and engineering can reach even the most remote corners of our solar system. Every encounter brings new mysteries, oceans beneath ice, volcanic moons, and atmospheres that defy physics. Together, they remind us that the quest to understand our cosmic neighborhood is far from over, and the greatest discoveries may still lie beyond. The next distant world.